Now we go to the Dr. ARIB Mehenna. Mr. ARIB Mehenna.
Bismillah ar-Rahman ar-Rahim. Can you see the slides now?
So you can start your presentation, Dr. ARIB.
Is it? Can you see the presentation now?
Wait a moment. Yes, it's visible, your presentation. You can start now.
Okay. Bismillah ar-Rahman ar-Rahim. So my presentation for today concerns the testing of the new code of practice for small fields, the TRS 483 at King Faisal Specialist Hospital and Research Center, within a group belonging to the IAEA, which was the coordinated research project. So I will try to present most of the results that we have. I cannot just present the results for the Elekta because it's still under investigation now. So for the code of practice, okay. So this code of practice was actually a result of 10 years of investigations done by a group of the IAEA and AAPM working group. This is actually the first time that the IAEA and the AAPM joined together to work on the code of practice. Every time the code of practice is published, we publish one from the IAEA and one from the AAPM, and it was a long fighting. For the first time, they could join together and issue a new code of practice for the international medical physics community. So this is actually a group, and this code of practice was tested by another group belonging to the mini centers worldwide, from America, from Asia, from Middle East. I had the honor to participate to this group, and which was really fruitful. And we had also the original group, Palmans, Faisal, and all of them were with us for testing this code of practice. This is a group in our King Faisal who participated, contributed to the testing of the code of practice. We have a Varian group, a Cyberknife Tomotherapy group, and we have now a new group for the Elekta. So when it comes to the dosimetry of radiotherapy beams, everybody knows the well-known code of practice TRS 398, which gives the absorbed dose to water, starting from one ionization chamber calibrated in terms of absorbed dose. So this chamber usually is calibrated in copper-16, and then you apply energy dependence calibration factor KQ0 to calculate the corresponding code of calibration coefficient for the high energy photon or electron beams. So the calibration is actually performed in reference conditions, particularly with a 10 by 10 field size. When it comes to the reference dosimetry, we have now. Previously, we had machines able to get big field sizes around, more than 6 by 6. But now we have plenty of machines, new and modern machines that can get what we call machine-specific reference fields, which is not necessarily 10 by 10. So we have the radiation generators having a field size of 10 by 10, and you have radiation generators which cannot achieve 10 by 10, like Cyberknife Tomotherapy. We have just small fields. In that case, we define the machine-specific reference field, which is specific to that machine. And so, in terms of formalism for static field size, we have the reference dosimetry, which you can see here, which gives the absorbed dose for this machine-specific reference field. which starts from the reading of the chamber, the calibration factor in cobalt, and you have here calibration conversion factor, which is similar to the TRS-398, which gives a calibration coefficient for the high energy beam starting from the cobalt-60. But now you have an additional factor which converts this calibration coefficient to the small field or to the machine-specific reference field. For the machine-specific reference field, we have for the conventional linear accelerators, we have 10 by 10. For the other machines like Brain Lab or you have 10 by 10 also. Cyberknife, the machine-specific field size is the circular field size of 6 centimeter diameter. For the Gamma knife, it's a rectangular field size, and for Tomo, it's 5 centimeter by 20 centimeter. This is the reference field size. So now we need to go and try to find out the way to measure the dose to water using that specific field size. And then when you move now to the, so this is what, this is the machine-specific reference field. Now when you go to the treatment on the patient, you have what we call the small field size. So just make a difference between the MSR field, which depends on the machine, and now you have the small fields, which are the fields that you are applying to the patients. In that case, you know that the tumor that does not have necessarily rectangular or square or cylindrical fields, it's arbitrary field size. In that case, you have to convert the dose that was measured for the MSR field to the dose that will be delivered to the patient. In that case, you apply what you call a field output factor. Previously, we used to calculate this field output factor as the ratio of the dose at a given field size divided by the dose at 10 by 10. When it comes to this small fields, it's a little bit tricky. So these are the steps to calculate the dose to the MSR field, as we said. Then you go to the dose for the F-clean, for the clinical field, which is obtained by the dose for the MSR field, and then you have the feed output factor. Okay. Now this feed output factor is a very important parameter, because this is the one that will give you the dose to the tumor that will be delivering to the tumor. So we obtain this factor as a ratio of the readings for the MSR, for the clinical field size, divided by the ratio to the MSR field. So this is the conventional output factor that we use to calculate. But when you take different detectors, and if you take the ratio of the dose at a given field divided by the dose at 10 by 10, you will have a problem for the small fields, because the ratio will be completely different, which can the difference can be up to 35 or 40%. So if you use for your calculation the conventional output factor, you will have the dose to the patient with more than 30%. So you can have another dosage. This was exactly the accident that occurred in Europe in the 10 years ago, when one medical physicist used to calculate, to measure the output factor using a big big volume chamber, and then all the patients that were treated with that output factor got another estimation. More than 30 or 40 patients were treated with another dosage. Yeah, and that's why the IAEA decided to go with the new code of practice dealing with the small fields. Okay, so this you have here. Remember, when you measure the dose for the MSR field, you send the chamber to be calibrated at the calibration lab, SSDL or primary lab, and then you calculate the calibration coefficient using the conversion factor. The conversion factor is given as a function of TPR. Okay, so the problem is that the TPR here is to a TPR 2010, which is, as you know, measured for a field size of 10 by 10. You cannot achieve 10 by 10 for the small, for the MSR fields. You cannot have 10 by 10 with the Cyberknife, neither with the tomotherapy. So this is the first problem. How can you calculate the TPR 2010, which is used to obtain your conversion factor for the dosimetry, reference dosimetry? And then secondly, we have another problem. We have a problem of the chambers. Which chamber are you going to use? Are you going to use the big volume chambers? Sorry, I'm not seeing the. You're thinking, yeah? Hello, can you confirm that is okay? Any confirmation, please?
Yes, your presentation lateral charged equilibrium.
Exactly. So now let's go and check which kind of ionization chamber are you going to use for the small fields. So a group of researchers tried to calculate the lateral charged particle equilibrium, which is one of the requirements for the application of the code of practice, because the dose to water is equal to the collision kerma when the lateral charged particle equilibrium is realized. You will see that for different energies, different beams, not all of them achieve, not all of the lateral charged particle equilibrium is not achieved for all the energies. You need to, it is achieved for a higher radius of the chamber for higher energy. So they came up with a formula which is FWHM, which is the full width at half maximum of the field size for that energy should be at least 2 times the lateral charged particle equilibrium radius plus the dimension of the chamber to be able to use this chamber for the dosimetry of the MSR. And this RLCPE is calculated by this equation using the TPR 2010 or using the percentage of dose at 10 given by the AAPM Code of Practice. Okay, let's go. And these are the MSR fields for the machine specific the machines like Cyberknife, Tomotherapy, Gamma, Brain Lab, Micro MLC, and with SRS Con adds on. Okay, you see that the MSR is different for each of the machines. And let's go with what we did at in our hospital. So these are the 3 machines that I will be exposing here. In addition to that, we have the Versa HD, Elekta Versa HD also. So here you have the Varian, you have the Tomotherapy, and you have the Cyberknife. For we use it specific phantoms for the True Beam. It's a big 3D scanner plus solid water phantoms. For the Tomo, we used also specific rectangular water phantom dedicated for tomotherapy plus solid water phantoms, and for Cyberknife also a water phantom, which is the blue phantom from IBA and the solid waters. Okay. These are the reference field sizes that we used for the specific machines. Okay. And these are the depth of measurement. Okay. Remember that for the clinical application, you need to use the field output factor, which converts the dose at the specific machine specific field size to the dose for the clinical field size. So you need to convert this using tables available in TRS 483, but these tables are giving the correction factors as a function of the S-clin, which is the clinical field size, which is the equivalent field size, which is given here for the Elekta Versa for True Beam and Tomo as the square root of A times B, A being the length and the width of the rectangular field size. Okay, and the condition is that A over B should be between 0.7 and 1.4. For the Cyberknife, it's given by R square root of pi. So you have to convert your field size to the equivalent field size. Use it for the tables. Okay, but to calculate A and B, you need to calculate the fold width at heart maximum to use it for the calculating the condition for the chamber and also for the actual field sizes. So these are the measurements we did for True Beam, for Cyberknife, and for tomotherapy. And we did also so look at this. You have for Cyberknife and tomotherapy, these are FFF field sizes. So from these curves we can calculate your fold width at heart maximum, and then I just display here. We worked to actually in parallel with the group of Saif al-Haq in USA. So you have here the cone diameter of the Cyberknife, and you have the fold width at heart maximum. The S-clean, the fold width at heart maximum calculated or obtained from the profiles. You see that you have a linear behavior, which is good for both our two groups. So these are the chambers that were used for our study. We have more than this, but I display here only for the True Beam, Cyberknife, and tomotherapy. We have the farmer chamber 06 cc just for the reference dosimetry in True Beam. You have the pinpoint. You have the semiflex, 2 semiflex chambers, and you have also the diodes, diamond chamber. You have the edge diode, and you have the IBA CC01. Look at the volumes; these are very small volumes. So we were asked to investigate the behavior of these chambers for small fields and to check the validity of the correction factors. When it comes to measuring in small fields, you have to pay attention to the position of the chamber, especially for small fields down to 1 millimeter by 1 millimeter. If the chamber is shifted from the center of the field, then you may have very bad results. So what is the way that we did for the small? We start with the small fields. We just scan from the right to the left and position the chamber at the maximum position to be sure that you are in the center of your field. Okay, and then for the TPR, remember the correction conversion factor for the absorbed dose calibration coefficient you need to calculate the TPR 2010, which is not available for the small MSR field sizes. So you need to find out the way to calculate the theoretical TPR 2010 from the TPR for the small fields. So we use this well-known configuration to measure the quality index for the small field. And then the Palmans in the code of practice gave this equation which converts the TPR 2010 for the small, for the MSR field or for the small field, and calculate the theoretical TPR 2010 for 10 by 10, which is used actually for calculating the conversion factor. So this is this factor is given either from the TPR 2010 or also there is another equation from the percentage that does at 10 by 10. So I have to go fast to catch the rest of the presentation. So these are the results that we obtained. Here we have the field size from 10 by 10 to 0.5 centimeter by 0.5, and then you have the measured TPR using the conventional method for measuring. You measure at 10 and 20, keeping the SAD constant and the field size constant at the detector level, and then calculated TPR using the Palmans equation. And this is the difference from the calculated TPR and the measured TPR for 10 by 10, which is actually the TPR for this machine. Okay, and you see that for the difference, maximum deviation here is 0.36%, which is actually very good. So these are the results for the Elekta. I give here whatever the results for the Elekta, and you have the results also for tomotherapy. As you can see, you have a perfect validation of the Palmans equation for field sizes from 10 by 10 to 1 by 1. But we had the problem with 0.5 by 0.5 which is considered a very small field. So the Palmat's equation is not valid for that field size. Okay, this is for chemotherapy. So now we have the TPR. So this is the second equation. If you use the AAPM code of practice, the quality index is given by the percentage depth dose at 10 centimeters. So we measured it also using the depth dose curves, and then this is what we got. We got a perfect validation down to 4x4. For 3, 2, and 0.5, the results were not that good. And actually, the Palmat's equation is valid only down to 4x4. Okay, because as you can see here, the field size should be between 4 and 12 by 12. So this is where we want just to check if the formalism is still valid for lower field sizes. Okay, so this is what we obtained for True Beam, and we have a similar result for the other machines. Okay, so now we have the TPR. Let's move to the second part, which is the FCLIN, the clinical dosimetry, which consists of measuring the field output factor. So the field output factor is actually calculated. So this is the output factor, our conventional output factor. But to get all the output factors aligned with for all the detectors, you need for each detector you need to correct for the field output correction factor, which is published in the TRS 483. So for each detector, you measure the ratio of the readings, and then you multiply for that specific field size, you multiply by the corresponding field output correction factor, and you get the field output factor, which is used for actually calculating the dose in clinical field. Okay, what the field output correction factor is given in the TRS 483 for all the detectors using this circular field diameter of the Cyberknife here. This is for Cyberknife, and this is for tomotherapy. So for Cyberknife, and this is for So you have for tomotherapy, for Cyberknife, and for conventional linear accelerators for field sizes from 8 to 0.4 centimeter by 0.4 centimeter. Okay, so there are some chambers that are not included in the TRS 483. We used to determine the field output correction factor for these detectors, and we are trying now to publish the results. So when it comes to the field output correction factors, they are given by this, and we in our calculation we use this equation to calculate systematically for any field size the corresponding correction factor using the Excel file. Okay, so these are the output measurement of the gamma or the field output correction factor. As you can see, we measured also the field output correction factor, the field output factor for SSD and SAD configurations. As you can see here, these are the field output factor for the True Beam, and we have, you have excellent consistency for the 3 detectors in True Beam, because here you can see that when you apply the correction factor, all the values are aligned. For the Cyberknife, we still have for Cyberknife we have good consistency for the Cyberknife within the uncertainty of measurement. So the field output factors are, the difference is about 5.9%, which is around the uncertainty on the measurement for small fields. Okay, and you can see here the ratio of the readings. When it comes to the ratio of the readings, when you take the output factor, the conventional output factors, which is the ratio of the readings from the field size S divided by the 10 by 10, the difference is up to 14%. When you apply field output correction factor, the difference jumped from 14 to 5.9, which is acceptable. For the tomotherapy, we still have some investigations which are coming actually from the fact that we use we started by using the solid water phantom, whereas you need to measure we have some problems with the tomotherapy because of the phantom. I will be explaining this. For the and just to display one of the results that we obtained, we checked the result of the feed output factors for the WFF and for FFF using the MLC and the JAWS. This is for the Elekta. We have a perfect correspondence, perfect coincidence between the result, which means that the procedure is valid for whatever configuration you use, FFF or WFF. Okay. So what are the lessons learned in our experiment? First of all, for tomotherapy, we had only 2D water phantom, which is available. Whereas for the LINAC or for the Cyberknife, you can use a 3D phantom, so you can scan in X, Y, and depth dose without any problem. For the tomotherapy, you need to put the phantom and then remove it, turn it by 90 degrees, and then you lose the accuracy because you need to really have the detector centered at the same center. The profile measurement for small feet takes longer time because of the required detector movement. If you scan for the small fields, if you go faster, you have the waves, the water waves will disturb completely your beam profile, and you get strange profiles. So you need to scan smoothly with down to 0.1 millimeter, if possible, per second. Very small movement. Okay. The SAD setup with water tank is not possible for tomotherapy because if you try to get the SAD, because the distance of the gantry, if you try to get the SAD, you will not get it. So we were not able to make the SAD configuration for the tomotherapy. The alignment and the positioning of the detectors in solid water phantom is very difficult. I showed you how to measure the alignment using the phantom. You need to scan smoothly and then go at the maximum. You cannot do this with the solid water phantom because then the only way to do it is just to take an image using the machine, if you have the imaging system, and then try to align your detector accordingly. And then the pinpoint, in our example, we use the two types of pinpoint, the 31106 and the 31006, which this one is not included in the code of practice. But the vendor taught us that you can use the same correction factor, which is actually not valid. So now we are investigating, checking the correction factor for that detector. Okay. For the TPR measurements, the measurements were performed for all the investigated field sizes. However, only two field sizes, 5 by 10 and 5 by 5, fit the table 16 given in the code of practice when it comes to measuring the equivalent field size. And then the interpolation of the field output correction factor can be performed using a polynomial fit for all data of the linear using the nearest field size without loss of accuracy, which means that if you have, for example, a field size of 5 by 5, you can use the 5. You can because it's the nearest field size. You can use the linear interpolation. When using ionization chamber, be careful to temperature and pressure measurement. It's very important because the error on temperature measurement for small detectors, it's terrible. If you have to put the thermometer close to the chamber in water and so on. Don't measure the temperature in air because you have terrible results. Here we display the uncertainty budget for the small fields. So as you can see, you have for the edge detector, it's 1.31% for the feed output factors. For the pinpoint, it's 2.8%. We developed within a group. We developed the methodology to check the uncertainty for the scanning for the small feet because you have to check the scanning. For example, scan the profile 5 times and calculate what will be the error in the profile if you make an error of 1 millimeter, depending on the phantom. So you use this methodology to obtain. Look, the uncertainty for pinpoint chamber is higher at 0.5 by 0.5. So for 0.8%, which means that the error in feed output factor around 8% is considered as non-significant because it's within the uncertainty. For the semi-flex, it's 5.9% maximum. Okay, and then using this uncertainty budget, we can decide whether the results that we obtained are acceptable or not. Most of them are actually acceptable. Just to mention that now we have a new step now, because we just purchased a new detectors, W1 and W2, which are from standard imaging centimeters. These detectors, if you go to the code of practice, the feed output correction factor for these detectors is 1, which means that if you measure the output factor, then you don't have to multiply by any correction factor. You consider this curve as ideal, which means that you measure with the W2 detector, you measure with any detector, and then you take the ratio, you derive, you issue, or you calculate the feed output correction factor for this unknown chamber in the code of practice. This is actually what we are doing presently. In addition to that, we are just now working on the implementation of the calibration capabilities for the small detectors using Global 16, to which we modified, and we are using Brain Lab collimators from 1 centimeter to 20 centimeter diameter, and then we are it's ongoing project. If we succeed to get this, we will be the only SSDR worldwide able to offer calibration for small feeds. Thank you. With that, thank you very much, and sorry for being long. Thank you so much.
Thank you so much, Dr. Arib. Please, if anyone have question, feel free to ask Dr. Arib. I think it's a very important presentation, Mr. Arib.
Yeah, Dr. Arib, I have a question.
Yes.
Yeah, I know that this is possible for you, but we have now ion chambers in our radiation therapy department. We have 3 ion chambers, and 3 for the photons and 1 for the electrons. And we are trying to send them to the IAEA for calibration, and that costs a lot. So, how about can we send it to you instead?
Yeah, for sure.
And how much will cost? You know,
we actually we calibrate actually the for radiotherapy in cobalt 16. We deliver NDW cobalt 16. It costs 3,500 riyal per chamber.
Around $1,000, right?
Oh, you have to convert.
Yeah, per ion chamber, right?
Yes. Any ion chamber. The cylindrical chambers, small detectors chamber like the pinpoint or semiflex, plain power chambers, roots, whatever. Just we have very well established calibration capability. The only, you know, that this is the only calibration lab in the region offering radiotherapy.
They used to have one in Syria, but I'm not sure if it is working still.
Syria, I think, you know, I think they collapsed, but they actually, I said we are the only one lab after the collapse of the Syria of the but, yeah, you can send them. There's no problem at all.
Yeah. Okay. So I'll ask our administration to send them to you instead of the IA. Thank you very much for the presentation.
We send you the service request.
Okay. Thank you. Thank you. Mr. Arib?
The hospital, my hospital will be very happy because I'm advertising for our service.
Zain Abidin, you have question? Yes.
Yeah. Okay, thank you, Dr. Arib. Doc, I am Shawi Zain Abidin. I am running a master program initiative. Sorry for the delay. Yeah. So thank you for all the organizer, and thank you for people who are contributing from other countries. Mohammed Saleh, we are sorry for this year. We will do that next year. So all of you are invited in CTF next year, inshallah. Dr. Ismail Zargougi is also with us. Good morning. Yeah. He will be with us next year, inshallah. I have a question for Dr. Arib. Doctor, just I have a PhD student who almost finished his work in Sporting, and we use it for that Monte Carlo as a gold standard to correct our chambers. Okay, so I have a small question. Okay, I really wish it that you add some Monte Carlo results on your last slides. That would be probably maybe more. I don't know whether if you can just use some measurements and you correct your chambers with the auto factor just by doing some measurements. What is your feeling?
Yes. Actually, our goal, the goal of this work was to test the IAEA Code of Practice TRS for H3, and as you know, this Code of Practice actually incorporates in the tables at the end of the Code of Practice, which is available for download. It incorporates the feed-output correction factors, which are actually the correction that you have to apply for the reading of your detector, whether it is an ionization chamber or detector ratio, and then you have to apply a correction factor to get all the output factors aligned. This factor, actually, the Code of Practice, in the Code of the group that started in 2010 working on the Code of Practice, they used to collect all the public data from 2010 to 2015 with all this data, where most of them, a lot of them were measured experimentally by comparing two detectors, one with known correction factor, another one without correction factor. But most of them are results using the Monte Carlo simulations. So you have to simulate the detector, the response of the detector for two different field sizes, the small field and the 10 by 10, and then derive the correction factor actually. So and then the group, they stopped applying, stopped writing the review of the Code of Practice in 2015. The correction factors that are incorporated into the Code of Practice are the ones prior to 2015. There are many published papers from 2015 up to now. They were not incorporated because they had to stop the Code of Practice. If you have a student, if you want, we can collaborate. I wanted actually to do many Monte Carlo simulations. We have one colleague from King Saud University who is excellent in Monte Carlo. We had another one in Morocco, Yemeni guy. We are trying to collaborate, and many of them they want to collaborate with us. But in our department, we didn't have no one good in Monte Carlo. That's why we didn't ask the Monte Carlo for our studies. We haven't published yet the results. I'm just waiting now. As I told you, we have ideal detector that can be calculating. I would love to have to do the Monte Carlo for our detectors. We have about 4 or 5 detectors which are not included in the Code of Practice, including the standard imaging A1SL.
Sorry. I have to tell you just, if you want to do that, I think you need a very good student, to do a Monte Carlo.
I'm willing to collaborate, and then your student also, he can incorporate the results. If we work together, if we achieve an agreement, then he can do the simulation, do the measurement.
Actually, we have finished the work. Okay. Actually, we finished the work. So maybe he will present his dissertation probably next month. Anyway, if you need, sorry, Steve.
Where?
جامعة الصيف.
Yeah, Steve.
Sorry.
Yeah, okay.
Plus, we can just ask him to contact me, and then we can.
Okay, last small question. Can you argue on the type B uncertainty, please? I would like to have, if you have done some models, you know, for type B. Yeah, please. You know, in Monte Carlo, we have not been able to do that, okay? To be honest.
The uncertainty, this is the most difficult part of the uncertainty calculations for the small fields.
Yes.
Why? Because the type B, as you know, this is the guesstimation of the uncertainty starting from the experimental measurement. So we consider 3 components for the type B, in addition to the conventional distance, temperature, correction factor, etc. But we have 3 additional uncertainties that we have to consider. The first one, it comes from the definition of the field size, the field width at heart maximum. You have to scan. So the uncertainty can come from the scanning system. So you have to perform different type of measurement just to evaluate the uncertainty. We developed within our IAEA group Formalism to calculate the uncertainty. I can send you the publication by the group but this you have to, for example, you have to open the field at, for example, 6 by 6, then scan 1 time, 2 times, 3 times, 4 times, 5 times, and then take the profiles. You will see that not all the profiles are coincident. They are not coincident. So you need to calculate what is the difference in the profile, beam profile coming from the scanning. In this case, the uncertainty that you have to take into account, this is the uncertainty on the scanning, which is some of the phantoms, they have 1 millimeter uncertainty. Some of them, they have 0.1 millimeter of accuracy. Then you have to stabilize the profile by 1 equation, and then you have, we derive the coming. Then you have another uncertainty. You put the chamber, you open the field size at 6 by 6, you scan 1 time. You open it and you close it to 6 by 6. You scan, open it, close it. So this uncertainty comes from the reproducibility of the job or the MLC. So this is the second uncertainty coming from the MLC. The third uncertainty can come from the combination of the two. So you need to put the field size, put the phantom 5 times, remove the phantom, put the phantom, pick up, and scan 5 times. So these are the sequences. We calculated the 3 components to see the type B coming from the scanning. This is one.
Yes, thank you. Yeah, good. Thank you.
Yeah.
Thank you, Abdel.
Okay. Abdel-Hai. Abdel-Hai.
ميكروفون عبد-الحي ميكروفون.
نعم. جيد استاذ ابراهيم، دقيقه لي من الافضل ديما اذا كان المتحدث نديروا ميوت كامل. تفضل استاذ ابراهيم، عندك لك الكلمه استاذ ابراهيم.
نعم، أنا بدي أول شيء I would like to thank you very much for inviting me to this seminar. It was very nice to see our colleagues from Africa. I have to go to another meeting, celebrations from the Asian part of the world. A happy Medical Physics Day for everybody. It was my pleasure being with you guys, and hopefully next year we will be face to face to see these nice faces and to be accustomed to you all. Thank you very much, and assalamu alaikum.
عليكم السلام.
استاذ ابراهيم كاين نجيبه بن شيخ سالت سؤال وما شفتوش. قبل ما تروح ماذا بينا نجاوب لها على السؤال. Why should we go for the CT scan when we have the PCR? I think this for you. I think this question.
Yes.
When we have PCR.
Why should we go for the CT scan when we have the PCR?
Okay, لأنه actually the PCR shows very good in the lung with using CT scan. Because X-ray could be, this is actually it's a clinical question. Radiologists will answer this. But from my observation, most of our patients, the COVID-19, they will take a CT scan because it shows very clear on the CT scan cuts. Whereas the X-ray, it only shows, it could be pneumonia or other things, but with the CT scan, it will show very clear the COVID-19, slices, and the physician will definitely, with the confidence that this is a COVID-19 patient because of the cleared images from the CT scan. That's why we use CT scan.
Okay. Thank you, Dr. Ibrahim.
Okay.
Thank you so much.
يلا السلام عليكم.
إن شاء الله السلام. نلتقي العام الجاي إن شاء الله أستاذ إبراهيم.
إن شاء الله. السلام عليكم.
السلام عليكم. شكرا جزيلا. منو عنده سؤال آخر؟ إذا عنده سؤال. أيوه إسماعيل زرقوق، عندك سؤال أستاذ إسماعيل.
Yes, I have just one question about detectors. What is the characteristic of the best detector for small fields up to now?
Yes, any kind of detector can be used for small fields if it fulfills the requirement of FWH full width at heart maximum more than the equation that I gave you. Let me the equation.
Yes.
Yeah, in this equation, you have to fulfill this equation, and then for this equation, I don't know if you can. I don't think that we have to. In this equation here. Sorry. Yeah.
Yes.
Sorry. Yeah. Okay. Can you see?
Yeah, I saw it. Yes.
Okay. In this one, you have. Look at this. The RLCPA. This is full width at half maximum. It is calculated for your energy. If you have, let's say, if you have a high energy X-ray with the TPR 2010 none. Okay. This it is TPR 2010 for 10 by 10, which is calculated. If you do the small fields, you have to calculate it using the Feynman equation, and then you multiply by 8369 minus. You get the lateral charge particle equilibrium. This will be more than 2 times. I mean, the foot width, the field size that you are using should be at least 2 times the lateral equilibrium plus D. What is D? D is the external diameter of the chamber. Be careful. Some chambers, they have the diameter is bigger than the length. So you have to use the dimension, the bigger dimension, whatever. If you have here, for example, the radius, just an example. If you have a radius which is 5 millimeter, but the length is 7 millimeters, so the D will be the length. Okay.
Yes. Yes.
So you have to go to the characteristics of the chamber, check what is the bigger dimension, physical diameter, and then inject it in the equation, calculate the lateral equilibrium radius, by 10, and get the field, get your field size, and then you cannot use any field size below this one.
Yes. Okay.
That's why, for example, the farmer chamber. If you go to the farmer chamber, you will find that the maximum field size is 6 by 6, or so, something like this. You cannot go down.
Okay. Another question: if you have, for example, a VMAT plan or IMRT plan, and you want to measure one dose point for the plant treatment, is that a specific chamber for that? Because we have a lot of small feeds, and we can't know what is the smallest one that we can deliver by the plan. So what do you recommend as a chamber for measurement?
Oh, yeah. Okay, you know, we arrived at the conclusion that the pinpoint and the CC01 chambers are very good for fields. You have also the detectors. Most of the detectors, the PTW detectors, are very good for relative measurement. And you have also the diamond chamber, which is very good. Be careful to the semi-flex chamber, because semi-flex chamber gave very bad result for small fields. So pinpoint, I think pinpoint chamber is very good. I think you have the pinpoint chamber.
Yes.
Okay. Okay. Thank you, Mr. Ali. Okay. Anyone have other question? Okay. I have question, Dr. Arib. When you decrease the field size, the difference between measurement and Monte Carlo calculation increase. For example, at 0.5 centimeter, you find 9%. في البداية, what's the objective to decrease the field size? What's the main objective?
You know, yeah. You know that for radiotherapy, there are some treatment like اللي كنت نتكلم عليه اسماعيل. For some treatment, you need, because the tumor, for example, the brain tumor,
Yes.
the very small, there are very small tumors. So you need to irradiate those tumors with very small field sizes. أولاً. ثانياً, we have some machines like the gamma knife. Gamma knife, the principle of gamma knife are cobalt-16 sources, different sources, and very small collimators that give very small field sizes, like 1 millimeter by 1 millimeter. So in that case, when you go to measure the dose for these small fields, you have a problem, because the chamber, it cannot be used for, you cannot get 10 by 10. If you measure the dose rate, the reference dose rate, الجرعة المرجعية, the reference dose rate for the machine, if the linear accelerator, the conventional linear, Elekta or Varian or Siemens, هذا ممكن you can get the 10 by 10 field size, and then you measure the dose rate on that field size, and then you go calculate the dose for small fields using the output factor. The output correction factor, this one is calculated as the ratio between the dose for the small fields divided by the dose by 10 by 10. So you have a problem of small fields. You need to measure the dose for the small fields. That's why you have to decrease the dose from 10 by 10 to down to 5 millimeter by 5 millimeter.
Yes, thank you. Thank you. Second question is how you calculate the difference. What's the rule? The difference is equal the measurement value minus the Monte Carlo value divided by the measurement value time 10%. This is the
comparison. We didn't do the Monte Carlo here. We didn't do the calculation here. But are you talking about the uncertainty? But if you want to compare, just for example, you have students who do the Monte Carlo calculation, and they do the measurement. How you can calculate the difference? Actually, it depends on what is the reference for you. If I consider my reference as the measurement,
yes,
then the difference is calculated as the calculated minus reference divided by reference. This is very important. I will explain why. And if you calculate the calculated minus reference divided by reference, in this case, if you get positive value, that means that the calculated value is more than the reference. So your calculation, your calculation is overestimated because you get plus. If you get negative, you underestimate. It's very important. This is not reference minus value divided by value. This is value minus reference divided by reference. Because حتى الساين إذا كان plus يعني عندك overestimation. إذا كان ناقص يطلع لك underestimation.
Of course, yes. But your reference, the reference is the published work from IAEA or
no, our reference is the published value actually. Yeah.
Okay. The last question, Dr. Arib, What do you think about using luminescent dosimeters such as TLD, OSL, RPL in the radiotherapy? What do you think about that?
Yeah. We are planning here. We have gaphromic films, which are supposed to be energy independence. Yani we can, for the output factors, we are measuring actually now. We are measuring for the cobalt-16 that I told you about. We are using the gaphromic. You can use the TLD also for the TLD, because for TLD, you know that the energy dependence of TLD is something like this. So it increases for low energy and then it goes stable for higher energy for cobalt-16.
The kilovolt.
That means that for the high energy X-rays, which are more than the cobalt-16, it's 6 megavolt, the energy dependence of the cobalt of the TLD is flat.
The reference.
So mainly published papers, they measure the output factor using the TLDs.
I have published paper about that. I published.
Yeah. We can use the TLDs without problem, but you need to pay attention. Don't use the TLD 100. Why? If you use the high energy X-rays like 15 megavolt, you have the contamination of the neutrons.
Neutron, yes, it's very sensitive.
You use the TLD 700 because TLD 700 is insensitive to neutrons.
Because the lithium 7 and the lithium 6, yes.
Yes, because
exactly.
So you avoid lithium 7 and it's not sensitive to neutrons. There's no sensitive. That's why you use the TLD 700 and TLD 700S. They are actually insensitive to neutrons, and then you can measure.
Of course.
If you use the TLD 100, then you will have terrible results coming from the neutrons.
Yes. The other luminescent dosimeters, such as OSL and RPL. Have you an idea about RPL?
We can also use the OSL.
Are you using RPL in your department? RPL, radio photoluminescence dosimeter.
We don't have the RPL in our lab, but the IAEA, we are participating to the intercomparison with the IAEA. They are actually now, they switched from the TLD to the RPL.
Yes, Japanese, yes.
This is also very interesting because the results for the RPL are much more better than TLD.
Thank you, Dr. Aib. Thank you so much.
You are more than welcome.
It's our pleasure today to be our speaker.
Thank you very much.
Thank you. Mr. Shawi, you are mute, Mr. Shawi. Mr. Shawi, are mute.
Just one remark, please. Look, regarding to your questions, look, if you want to understand exactly why we have to use Monte Carlo for small field or measurement for small field, I think the better thing is that you have to read the new code, which include now the TRS, this for small field. So I suggest that for the clinician in Nigeria should read first the new code of practice, including the small field. Then you can understand why some people are using experiment in their measurements or Monte Carlo calculation or both. So we have 3 methods inside, and they are accepted now, okay, by the international community. But you have to choose which one is the best for you. If you have very good students, you can use only Monte Carlo starting from the phase space of your center, not those of the agency, okay? And then you start to do that and then correct the ionization chambers you want to do that. But if you want to do experiments like the ones presented by Dr. Mehenna ARIB, this is something else. And most of the time we don't compare them, we don't, let's say, match between the 2 methods. It's not well, unless if you just say that you want to use Monte Carlo as standard, like gold standard, and then you start to compare to other. But first, you have to understand why it's important to use Monte Carlo in small field, and then the physics, why the field will change when it's less than 3 by 3, for example. And then you can easily understand why we need for this new, let's say, code of practice. So I think that the better thing is that I really want that the clinician in Nigeria read first this new code for small field. And thank you.
Thank you very much.
Thank you so much, Professor Shawi. Okay. Now we will, okay, you can deactivate your presentation now, Mr. ARIB. We will go now to the third presentation by the student Hidayah Belwi. Hidayah Belwi is a student of Dr. شاوي زين العابدين and one of أيوة تفضل أستاذ.
I have to me also to move to another meeting with the IAEA regarding the
yes.
Then I will try to come back.
Yes, in the Dubai. يلا ماذا بينا أستاذ ترجعنا للدبان بعد إن شاء الله. You are free, Mister. You are free. Thank you so much.